right, let's go ahead and start our energy unit. This is going to be our first part of our notes, so let's go ahead and get started. Let's talk about the relationship between energy and work. Whenever work is done, energy is transformed from one system to another system. Just like when we talked about this last unit, when I'm pushing a desk, energy is transformed from me to the desk. Now, energy is the capacity to do work, and energy is measured in joules. And the way I remember the energy definition is that I have to have energy to do work. So the capacity or the ability to do work requires energy. Now, let's look at mechanical energy. This is a type of energy we're going to discuss. We're also going to discuss non-mechanical energy. So let's look at mechanical first. Mechanical energy is the amount of work an object can do because of the object's kinetic and potential energies. Now, there are two types of mechanical energy that was mentioned in the definition. We have potential energy and we have kinetic energy. So let's talk about those in a little more detail. Potential energy is sometimes called energy of position because it results from the relative positions of objects in a system. For example, this is the definition. The potential energy is the energy that an object has because of the position, shape, or condition of the object. And any object that is stretched or compressed to increase or decrease the distance between its parts has elastic potential energy. So an example of that would be a rubber band. When you stretch it out, to increase the distance between its parts, then it has more elastic potential energy. And so another example would be bungee cords. Now, any system of two or more objects separated by a vertical distance has gravitational potential energy. So we have mechanical energy, and mechanical energy has two types of energy, potential and kinetic, and we're talking about we're talking about potential. And so potential energy has two forms. We have elastic potential energy and gravitational potential energy. An example of gravitational potential energy is a roller coaster at the top of the hill before it starts descending. That means that the roller coaster has a great or a large amount of potential energy. Gravitational potential energy depends on the mass of the object and the height of the object. Now let's look at kinetic energy. Kinetic energy is the energy of an object due to the object's motion. So a lot of times this is called the energy of motion. Kinetic energy depends on the mass of the object and the speed of the object. So make sure you know potential energy depends on the mass and the height. Kinetic energy depends on mass and speed. Kinetic energy, however, depends more on speed than it does mass. Atoms and molecules have kinetic energy. You should remember this from our first or second unit. When we talked about how molecules move in solids, liquids, and gases, the more you heat them up, the more the temperature increases, the more kinetic energy they have, so the more movement they have. Now let's look at other forms of energy. We have non-mechanical energy, and this is energy that lies at the level of the atom. In most cases, non-mechanical forms of energy are just special forms of kinetic or potential. So they're kind of similar, but they're just in different ways. Now, chemical reactions involve potential energy. The amount of chemical energy associated with a substance depends in part on the relative positions of the atoms it contains. So chemical reactions have potential energy and that result in chemical energy. Living things also get energy from the sun. This is another type of energy. Plants use photosynthesis to turn the energy in sunlight into chemical energy. So we've already talked about non-mechanical energy being at the level of the atom and having chemical energy in a chemical reaction. Living things actually use the energy from the sun to transform into chemical energy. And the sun gets its energy from nuclear reactions taking place in the core, in its core. And that's how it continues to produce so much heat. Now, energy can be stored in fields. And I'm not talking about a cornfield or a cotton field. I'm talking about electrical fields. Electrical energy results from the location of charged particles in an electric field. If the charged particles are lined up correctly, then you have electrical energy. When electrons move from an area of higher electric potential to an area of lower electric potential, they gain energy. And this is an example of when we were talking about the other forms of energy and the non-mechanical forms of energy are still different types of kinetic and potential. Now, light is also energy, and light can carry energy across empty space because light is photons, which is energy. Now, light energy travels from the sun to the earth across empty space in the form of electromagnetic waves. Electromagnetic waves, in a couple of units, we're going to actually learn a lot more about. Now, electromagnetic waves are made of electric and magnetic fields, which is what gives it its name. So just remember, electromagnetic waves mean you've got electric and magnetic. And so light energy is another example of energy stored in a field. So we have electrical energy stored in a field and light energy stored in a field. Now, there are changes in energy. Energy, like we said at the beginning, can be transformed into many different forms. For example, you have light bulbs. Light bulbs have electrical energy coming to them initially, and that electric energy then transforms into light energy and thermal energy. Because if you touch a light bulb when it's on, you see the light, but you also feel the heat. It actually can burn your hands. So it starts out as electrical energy, and that energy transforms into light and thermal. What about an alarm clock? Alarm clock starts with electrical energy coming from the outlet, and it turns into light and sound energy, right? Because you can hear the alarm going off, and the time is reflected by light. Now, fuel that you have in your car stores energy in the form of chemical energy, and the engine transforms that chemical energy into kinetic energy so the car can move. So you have to be familiar and be able to take an appliance or a machine and tell what type of energy is transformed and how that works. Now, let's talk about one more thing, law of conservation of energy. This is saying that energy cannot be created or destroyed. So energy does not appear or disappear. Whatever energy we have at the beginning, we have at the end. It just may be in a different form. Now, in regards to law of conservation of energy, there is a way to see if energy is conserved or not, and that's when you use an isolated system, because energy can't be released in an isolated system. However, to explain how sometimes you think you've lost energy, we're going to look at the different types of systems. An open system is when energy and matter are exchanged with the surroundings. So a lot of times in an open system, energy leaves what you're using and it goes into the surroundings. So you think you've lost energy, but you haven't. It's just been transformed and released into the surroundings. A closed system is where energy can be exchanged but not matter. And in an isolated system, neither energy nor matter is exchanged. So I kind of think about it like as a classroom being closed or open. If our classroom has the door open, we would consider that an open system. Energy and matter can go in and out, in and out. Now, a closed system, when we have our door closed and locked, energy can leave and come, like our light from our classroom can actually go underneath the door and be seen from the hallway, right? Or light or sound can come from the hallway into our room underneath the door. And so energy can be exchanged in a closed system, but matter, like I, cannot walk through the door unless I open it. So matter cannot be exchanged when we have our door closed in our classroom, but energy can be. And then an isolated system would be where we close the door of our classroom and that every little crack is sealed. So there's no space underneath the door, on the sides of the door, that everything is completely sealed. off so that energy nor matter can be exchanged. All right, that concludes our video for tonight, and this is what I'd like you to do. You actually have a little bit of space, and I'd like you to write a small letter to an absent student. Pretend like it's your job to fill in a student from being absent and tell them what this video is about. So go ahead and write that down on your notes, and we'll see you in class.